Good evening and welcome to the talk on terracotta. We're very lucky to have Patrick with us, who's doing a PhD looking into the properties of terracotta and perhaps how we might look at firing terracottas differently over the years. And I'd just like to start initially and say why we've got Patrick doing this PhD. And it came from initially having surveyed Harrods and terracotta from about 1985 onwards, and also looking at various other terracotta buildings around the country, that there was some areas that we needed to improve. And this was confirmed when we wrote or helped put this book together, which is the Earth and Terracotta Best Practice series produced by English or Historic England. The previous ones were English Heritage. It's a 2-volume, but they're too heavy, so I only brought one. But in there, putting that together, identified how little we actually appeared to know about the production of terracotta and the effects of making changes. So we've got Patrick here to do this research, and we've been very fortunate that Harrods have helped by funding or part funding the research project. So that has been brilliant because they not only have the terracotta, but they give given us some money. Patrick.
To grab you some water. So, good evening. I've got a much smaller book with me. For those of you at home who can't necessarily make out the full scale, the Historic England Part 1 of 2 is about 3 kilos and can kill a small cat if you drop it at the right angle. This one is a print off of McIntyre's 1929 survey of terracotta in the UK, which, as far as I can work out, was the last time a systematic survey across the industry was done. And at the time, he was looking at new material, which then rapidly went out of fashion, what with the wars, and it was never really followed up on. But it means that his book is looking at the same material that we're looking at now, nearly 100 years later. And there's some very nice comparisons we can do, and I'll come back to that in a minute or two. Terracotta. Today, we're looking mostly at porosity. I have given a previous talk at the 2023 Terracotta Conference at Birmingham City University. That was focused on the chemistry and fireskins and possible mechanisms for fireskin formation. So if that's what you're really interested in, I'm really sorry. You'll have to wait for the paper. If you would like to write to the academic journal, I can give you the name at the end and tell them to hurry up, because it's sitting there waiting for someone to review it. And the work today is based on sponsorship by, as Michael said, Harrods and the University of Bath. They've been incredibly accommodating, as has the entire industry. It has to be said. It's been an absolute pleasure to work with everybody so far. Structure of the talk: background, 10 minutes, research, 20 minutes, and a case study to bring it together, 20 minutes. I am terrible at keeping on time. I can talk for hours, quite literally. So let's see if we can keep this going. Why porosity? So there's 3 things in particular that kill terracotta buildings in the UK: ice, salt, and to an extent, biological growth and algae and forms like that. The picture there is actually of moss, which is fairly innocuous in terms of damage, but biofilms aren't very photogenic. It just looks like black smeared stuff on the terracotta. So that's what you got. So that picture on the far left is from a different site. It's not going to be mentioned again tonight. But what happened there was that was a fairly new piece of terracotta, nice finial up on the roof. It'd been put in the 80s, and it'd been put in using a 1980s sort of chemical epoxy. The chemical epoxies are very thick, and that terracotta was very, very, very well vitrified. It had almost no porosity, and there was almost no suction. So when you're building a wall with bricks, you're relying on suction to glue the bricks and the mortar together. And in this case, that finial had sat up there on top of that epoxy mortar under its own self-weight for about 20, 30 years until it blew off. And we went up and we checked all the other ones on that building, and they were all loose. They were just sitting there. So some porosity is useful. It's necessary. That picture of bricks there, that's definitely freeze-thaw damage. That's a classic garden wall damage. But the pattern of the damage, that very flat spalling, that's where there's a slip plane. So when the bricks have been extruded, there's a slip plane where that skin is dragging during extrusion. And a few millimeters below is where you have this long streak of pores, and that's what's cracked as it's filled with water in the icy cold Cardiff winter. Well, soaking wet Cardiff winter. So that particular failure mechanism is also due to a defect in the brick manufacturing process. It's not just the ice that's at fault there. That another picture there is of salt appearing on a brick. And it's not a huge surprise it's appearing on the brick because I poured salt into it. But it's sodium chloride. That's just table salt. And I used that because it was handy and it was in my kitchen and it was the weekend. But sodium chloride only expands a little bit as it dries. Some of the other salts expand a lot more. And if you're in the real world situation, you have a mixture of salts and they come out of solution at different humidities and at different concentrations, depending on the other salts that are present. It's an absolutely wicked problem. There's some lovely work going on in Belgium looking at it. So it's not just the fact there's salts present, it's which salt and how is that interacting with those pores. And that final one there is a biofilm. I told you they're not very photogenic. But that's another garden wall, and it has two different types of bricks. That classic one where you got that low wall that everyone trips over, so they add another 4 courses on top, so then you can lean on it instead. The bricks have got slightly different roughness and slightly different porosity. Course on top is absolutely covered in biofilm all the way along the wall. The courses below aren't, and have a few traces of biofilm basically hanging down from the bricks above them. So it's exactly the same exposure, it's exactly the same water exposure, exactly the same sunlight, and exactly the same species. It's only the difference between the bricks that is causing them to grow there or not. And that's not necessarily the porosity, it's also the surface roughness, which is causing the water to spread, causing the giving the algae basically something to grip onto, at quite rough scales. I think you'd call them gritted bricks or possibly water struck, depending on where you're at. So I'm just setting up a few caveats before we start the rest of the talk. Right, fireskin. It's a classic part of terracotta. It's the thing you always see referred to in the conservation documents. You must not damage the fireskin, you must not abrade the fireskin, you must not cut the block because you will ruin the fireskin. The fireskin has never been formally defined. Please check my upcoming paper. But what I have done is I've split it. I've talked about enhanced surface toughness, reduced surface sorptivity, which is basically thirstiness. I did an entire stall at a child's science fair called Do Bricks Get Thirsty? And enhanced chemical inertness. That little green one in between was suggested by an engineer at Harrods, and it's resistance to staining, because that was really bugging him at the time, pigeons in particular. I think resistance to staining is basically a product of the sorptivity and the chemical inertness. I haven't really looked into that yet. If you're an up-and-coming person, that might be something to look at. And I've split those mechanisms because different fireskin production mechanisms strengthen some parts more than others. And some buildings seem to need the fireskin more than others. The famous case is the Albert Hall, which was sandblasted. It lost everything. People said, oh my goodness, it's going to fall apart. And it just sat there. It did not care. And as far as we can work out, it's because it was fired to it was a particular clay blend that was fired to a good temperature for a decent time. And so all the way through, the cross-section was well developed. And the cross-section, even at the middle, might be stronger than the fireskin on some of we just whacked it in the oven for one day, blocks that were coming out in the early manufacturing. Why sorptivity? So sorptivity is again, it's that measure of thirstiness. You've got the pressure head pushing water into the building. So if you've got a strong wind, a driving wind, there is actually something pressing that water in. You have the capillary suction of the pores, and we're talking at very, very fine details here, very small pores, so very strong capillary suction. But we also have drag. And as long as those forces are unbalanced, the water accelerates. And as soon as that drag starts to pick up to the level it balances the other two, the water stops accelerating, but just continues flowing into your building. Of course, in reality, it's not one pore, it's not one straight line. We've got a whole mess of things going on there, and it slowly spreads from the water source into the terracotta as like an expanding dome, approximately. The finest pores, the water moves faster. The bigger pores, the water moves slower. Behind that wet front, where you've got saturated terracotta, is the biggest pores that deliver the water onwards. They're like the motorways, if you like. Okay. Any questions? 5 minutes over schedule, which is 50% of the way. So I would, this is just some sort of essential background. You don't necessarily need all of it from what's coming up, but it should make it slightly more. Just keep going.
Sorry, this is one thing. Is it possible just to do a very quick definition of what is brick terracotta? Why you go?
No. That is the second time in 2 days, and the other one was on a pub crawl in Manchester, and he said, can you do it in less than one sentence? And the answer is no, there isn't a good definition. It's a very, very fuzzy spectrum. Right. At the end, because that is also not correct. It's mostly correct, but not universal. Methods. We're going to get through this really quickly, I promise. This is the slightly detailed bit. This is where a lot of my work in the PhD is. And it's possibly of less relevance to you if you're working on site and if you're doing specifications. If you want to specify terracotta accurately, and you want to say we need this particular type of terracotta or this porosity matched or this pore distribution matched, then the method you use to measure it will give you slightly different results. So knowing which method you're specifying that they need to meet is probably worthwhile knowing. The other thing is that I've gone through a range of equipment, from the really expensive fun things I get to play with at the university, to the absolute cheapest, very suitable for heritage groups and volunteers, and things that doesn't matter if I accidentally stand on it while I'm on a scaffold. CT scanners. So these should be familiar from hospitals. You put the patient in, they get scanned, and it produces that 3D volume, which you then go through in slices. So the starting image for this presentation was 4 little samples in one scan. The largest of those samples was about 5 millimeters cubed. So we're talking very, very small samples for what I'm working with. Each one of the pixels in the picture is about 16 nanometers. And to be honest, I'm actually talking about the original picture. because PowerPoint has done a compression job on this and it's a lot blurrier than it should be. But it does show us a lot of lovely details in this particular sample of glazed terracotta. So we can see the individual bubbles in the glaze. If you look at where you've got these sort of big white blobs, they're the quartz. And where you have the quartz, when it gets hot, around about 576 degrees, it changes crystal structure and expands slightly. And then as the terracotta cools down again, it shrinks slightly. That's why potters and ceramicists make such a big deal about heating up and cooling down slowly. Because if half of your sculpture or half of your brick changes size and the other half doesn't, it tends to rip itself apart. And you've got to start all over again. But inside the structure, where those crystals have shrunk, they have left that gap behind. That's very characteristic. We've also got straightforward pores and gaps left where the materials wasn't compressed solid in the first place or is shrank and compressed. And we can also see examples of pieces which are fully connected. There is no shrinkage gap around them, so they're not quartz, but they are noticeably different in density. And that would be another piece of ground up ceramic that's been added to the terracotta before firing. And that helps with dimensional stability. Because it's already been fired, it doesn't tend to shrink. So it remains well bonded. And dimensional stability is quite important for terracotta, much more than for art ceramicists and teapots, because you need to fit, the thing needs to fit the building, and they're quite big. So 10% shrinkage on something that's 300 mil long is 30 mil. That's something that's actually quite hard to lose within your mortar joint if you've got it wrong. MIP, this stands for mercury intrusion porosity. And basically, mercury does not like going into things. If you've ever broken a thermometer, it just rolls around as quicksilver. It forms the little beads floating on the surface. It will go into things if you put it under enough pressure. And the hole it will go through, the size of the hole it will go through is dependent on the pressure you're putting it under. So you can put a small sample in the machine and slowly turn up the pressure and measure the volume that has been pushed into it at every stage. And these are very small samples. These are 5 millimeter blocks or smaller. And even with 5 millimeters, you get a pressure differential between the top of the sample and the bottom of the sample, which will start to blur your data a little bit. It's also destructive because afterwards you've got a lump of terracotta with mercury in it and nobody wants that. So this was a sample of typical good terracotta. This is one off Harrods. And as you can see, we've got one massive pore in that big red spike at the start. And that's probably just an air bubble on the surface of the sample. You can largely ignore that. And then as we go down increasingly small pore diameter. So on these charts, for some reason, as you go left to right, the pore diameters get smaller. You can see it's mostly clustered around the middle there. The blue line is the average in my data set. So that allows you to compare it to all 40 or 60 pieces I've put through. And you can see it's got much less fine pores than the average. This one is off the Glassworks. This is a not so good quality terracotta. We'll come back to the Glassworks, but you can see there's a huge amount, more volume associated with those fine pores. The graph is much higher on the right-hand side of the screen. I'm seeing some frowns in the audience. Is everyone okay with this? Buoyant density, much more classic. In fact, it was used in 1929, exactly the same way, which allows us to do a comparison. Basically, what you do is you get your sample, you make sure it's dry by putting it in the oven for a week. You measure its weight. You put it in a vacuum pot, you drag all the air out of it in a vacuum, you add de-aired water, you get it nice and wet, and then you measure its wet mass. Strictly speaking, You get it out the pot, you carefully dab it dry without leaving water on the surface or without sucking water out the body, and then you weigh it. There's a little bit of error associated with that method. And then you measure the weight of it wet while in underwater. And you can do the calculation across those three masses to work out the apparent relative density and the apparent porosity. And the apparent here means it including the closed pores, but excluding the open pores. So if you think back to that CT picture of the glazed terracotta, it had those little closed bubbles in the glaze. Doesn't matter what you do to it, if you put it in a vacuum pot or not, you soak it for a week or not, no water will be getting into those bubbles. They will be making it look less dense than you would expect. It'll be floating a bit like a boat. So that line on top is historic terracotta measured in 2024. This is a reduced part of my data set. I've stripped out anything that's more modern terracotta. I've stripped out anything that isn't strictly terracotta, that is in there to provide balancing points like bricks and tiles and things. The grey triangles underneath are McIntyre's original data, converted out of imperial units. And it's a very interesting comparison because the apparent porosity doesn't seem to have changed much. The medians are almost perfectly aligned. And the sort of upper and lower limits actually look about the same place as well. But the old terracotta samples I've tested this year appear to be heavier now, denser now, than they were when they were being testing a bunch of samples of new terracotta in his lab in 1929. So that purple line, I looked at like the open porosity. I said, well, if we have stuff accumulating in the open pores, and I used calcium carbonate for the test run because it's a classic white fluorescence that builds up on brick, and it's very familiar to everyone. And also it doesn't dissolve, which means it would stay there in the vacuum test. Some salts would actually dissolve out quite quickly, so they wouldn't appear in this test. But if you're adding stuff to the open pores, you change the apparent porosity as well as the density. That's that purple line, which is trending slowly upwards. If you're talking about the closed pores, those sealed off areas cracking open over time, then the apparent porosity should be increasing. If you want to move the one median from 1929 up to the median of now, 2024, you need those two processes to be perfectly balanced. Or, as I was thinking about on the train, we need some sort of mechanism which has stuff accumulating in the closed pore only. Now that's an interesting problem. If anyone's got any ideas, can you talk to me afterwards? Another method, this is a simple method suitable for school children. You get your terracotta, you put it in a suitable tray. I use takeaway trays. You put in a lot of salt and water up to halfway up it, and then you wait to see where the salt pattern emerges. While there's water in the tray, the salt is appearing where the water is evaporating from. So it's tracking the location of the biggest pores, the motorways through the terracotta. This one was interesting because that crack was there from the very start. That was in the terracotta when it was fired. And if you look down at that bottom left image, there's actually not much salt appearing around that crack. We basically have an internal fireskin developing. Now, this isn't a particularly robust method for quantitative results, but it's very good for qualitative results. If you want to compare the body and the skin of a piece of terracotta, you can put them side by side in the same tray, same conditions, you'll see how the salt appears. The other thing that was really interesting with this was that when I took them out of the water and I left them on the windowsill to dry, I do have access to a lab, but windowsills are handy. The salt pattern reversed. While they were drying, anywhere there was salt didn't have any appear. Anywhere that had no salt at the time was where the salt started to appear from then on. And that, as far as I can figure out, is because we're looking at cases B and C. Yeah, so B, we've got that saturated flow. There's always more water coming, so the biggest pores that it can flow through with the least drag, that's where that sort of salt buildup starts to concentrate. But when you've got drying, it's the smaller pores have got that capillary suction. They hold on to the water and they drain it down from the bigger pores. So that if the evaporation is only happening at the surface, then it's your smaller pores, which is where the salt's going to occur. And this is really significant for heritage building. Because if you've got a building that's soaking wet and getting damaged, and you fix the gutter, you will get a new patch of damage appearing where it wasn't. Because you have changed from a wet saturated flow to a drying situation. And I'm getting a few nods at the back, which is really relieving. I've had them every single time I've said this. One day someone is going to say, no, that didn't happen. But that is one of the more sillier results from a takeaway tray and some leftover salt. It's quite an interesting model. Casting tubes. This is the last, almost the last of the methods. Promise, we're nearly there. And what these are really simple. It's basically a pipe. You press it against the block with a bit of plasticine. You then fill it with water and you measure how fast that water goes down until you run out of time, you run out of water, or it falls off the block. And believe it or not, that's an actual quote from an academic paper in Italy describing their method. What I've been able to do, because I'm working with small samples in the lab, is I can directly put it on a cut cross section. So I can put it straight to the body, or I can put it straight to the fireskin. So we can compare those two very straightforwardly. I'm also able to use decane as well as water. So water is a little bit more common in the environment. Decane is basically a slightly polished up version of petrol, but it's not polarized. So if you have a fireskin effect going on, knowing if it's because of a chemical polarity, which is repelling the water, like a waterproofing or like a biofilm, is interesting to know. Biofilms tend to be hydrophobic because they like to keep the water in their rock in the rock. So they want to prevent that water escaping in their natural desert environment. Here's an example. So this is plotted against the time square root seconds. The maths teacher in the room has just crooked an eyebrow. It's slightly more straightforward than a log plot, but it's effectively the same thing. But what I'm able to show is for that one on the left, which is again actually a Harrod sample. The body, the green dots are rising very quickly. The skin, the blue dots, are rising slowly. And it's the slope of the graph that gives you the sorptivity. So it's very clear that the skin is absorbing water more slowly than the body is. There is some sort of fireskin effect going on there in terms of sorptivity. On the right-hand side, the Victoria Palace Theatre, which is actually a glazed terracotta, but this is a sample cut from the back of the block, so it was never glazed ever. We're showing that the glazed skin and the actual cross-sectional body have exactly the same results. And if you note, it says also with area corrected as well, because one thing I have found with casting tubes is that plasticine does not squish particularly accurately and you get a variance of up to like 15% in area, which is quite enough to make two different samples on the same block look very different. So do correct for it. Air permeability. So this is a bit like the casting tubes, except instead of pushing water through with a little bit of pressure head, we're basically putting it in the lab and getting a big canister of air, rubber seal, press it down, blow through. And this was done by Professor Murilo Innocenti with his students over in Brazil. He's a visiting professor at Bath, and this is his speciality, this form of testing. So what we've been able to do is map permeability on these big samples. And because air is much more fluid than water, he was able to get data for ones I basically reported with the casting tubes. There's nothing going in. So with his data, we can do things like that. So we can map the permeability on the block. That's using a nice little Python add-in, but I'm sure it's available in R as well. The thing that I found really interesting here is that looking at the block itself, the picture up at the top, you know, if you had to ask me where's the permeability going to be high, I would have said that damaged side. Where's it going to be low? Oh, the good side on the left. And it's not really strictly clear. A lot of the surface damage is quite often superficially surface. Quite often cracks or visible holes were there when it was fired. And at the microscopic levels we're talking at, the terracotta is sealed on the inside of that crack. It's just a continuation of the fireskin. So the visible defect doesn't necessarily tell you much about how it's performing, which is a bit annoying. Right, we should be 30 minutes in. How are we doing? Yeah, with 35 minutes in, I'm keeping time. Everyone okay with that? Cool. Any questions? Right, rocketing on. Any questions on the internet? No. Right. So that was some of the methods I've been using in my PhD. It's not all of them. It's just the ones related to porosity. It's just some of the ones related to porosity and the ones that are generating more useful results or are more applicable to things you can take to site. If you like casting tubes, ask me and I'll send you the STL for 3D printable ones because they cost about 20p each to make. And therefore it doesn't matter when you drop them off the side of the scaffold. Also, they're made of plastic and it actually doesn't matter if you drop them off the side of the scaffold, unlike the glass ones. So, case study, Glassworks building. So I'd had my eye on this building for a while. This picture is after the restoration, so there is a happy ending, just to spoil all tension in the room. It's a Bath limestone building. It has a pub in the bottom and it has flats of supported accommodation above it. It had some surprise terracotta. The mouldings, those little curvy bracket bits supporting the cornice, were made of terracotta. Surprise. Does anyone have any ideas why? No, I don't either. It's the Glassworks. It's a building over in Cardiff. I'm not a Londoner, I'm afraid.
Well, it's clearly going to be cheaper than custom one of those by stone if they're all going to be the same.
Yes, but the ones around the corner are stone.
They're different in the building they do. Unless they're being
I think that's a matter of how they were repaired. The client brief wasn't for detailed historic recreation.
They've actually done the same thing. The museum in the Oxford, when the brackets are terracotta and the building is stone.
Interesting. So it has occurred more than once. I was wondering if it was they had a sale on at the builder's merchant or something. Yeah, but there was absolutely nothing in the records.
The core ones on that building, the
Can I be a voice of God and suggest we defer the discussions till the end when we can get the mics on everyone, because those of us outside the room can't hear the question.
Oh, sorry. Yep.
That's fine. Or
Okay,
else
so
repeat the question. That's all.
We'll go back to that, Patrick.
we'll go back to that.
Yeah.
Right.
Thanks
So
very much.
the photo is showing after the restoration. Would you like to see it before? So that was why I knew it was terracotta, because even from street level, I could see it was hollow. And when I saw the scaffolding go up, I rang them and said, "Can I come and have a look at your terracotta?" And they were incredibly helpful, bless them. But the exact words were, "Oh, it's terracotta." We were wondering why someone had hollowed out the stone. When you got there, you could actually see the finger marks still baked into the clay inside. It was a pale pink terracotta. Pretty much all the moldings were in this sort of level of condition, one way or the other. I thought of giving you more photos, but frankly, they were all in this condition, except for the one that was full of bees. The cornice they were supporting had a gutter, and that gutter was blocked, as they tend to be. So as you can see, they're quite wet, and they're actually slightly damper, I think, than the Bath limestone around them. I was allowed to take a couple of samples from these, and I ran them through the tests we have at the university. So that MIP, that graph, familiar? So again, we've got, compared to the average terracotta. Now bear in mind that all of my samples have been removed from a building for some reason. So I'm probably not working with the best stuff. It might be things that were removed because the steel behind them corroded, or because they needed to put a vent in or something. Quite a lot of my samples came to me quite damaged. Even compared to them, this has got a lot of very, very fine pores. And it pretty much tracks the average on all the larger pore diameters as well. So we're talking very high porosity, very high fine porosity. And the material was like a powder. When I say I took a sample, I could pull it off with my fingers. So at this point, I was thinking freeze thaw. Yeah, seem reasonable. Blocked gutter, everything's saturated. Something happening inside it that's caused it to break down, open up a lot of fine pores and micro cracking. But I also ran it through an EDX analysis. And that's a really handy, very expensive machine we have that you can put a tiny bit of powder in, and it will give you the atomic ratios of all of the elements present. We have other things that will give you crystals and certain types of bond, but they have their own issues. I can talk about that at length if you want. But for EDX, I like it because it tells you there's this much aluminium, there's this much silicon, there's this much oxygen. It's a fairly simple and robust analysis. In the sample near the skin, there was calcium and sulfur present, which is a bit unusual for terracotta. A few millimeters further back, where the material is a little bit better, that calcium and sulfur was a little bit lower, much lower, in fact. Still more than anywhere else in the data set. So what are the implications for the repair strategy? And if people say things to me, I will read them out so they go on the internet as well. And if people on the internet have ideas, please be a voice from God. So what's causing this terracotta to break down? And if you just replaced it like for like, will it break down again? Anyone want to hazard a guess?
Yeah, I will. Says the voice from
Yay.
God. It's trapped air. This is the thing we keep forgetting when we're talking about these materials. But I think that's something we should discuss at the end when we have a full discussion about where we go with testing.
You think it's trapped air?
Oh, I'm sure of it.
Oh,
Mhm. We don't take enough account of that in our testing. We tend to test wet samples. And in fact, the question I have to ask you at the end is are we overvaluing the value of testing by, for instance, putting pieces in trays where, of course, they can saturate because the air is driven off, whereas when you have things in situ, the air cannot get out so easily. Air pressures can become very, very high, and unlike the salt pressures or the ice pressures, but for instance, ice we know can compress the air in if ice is coming from two directions, hence freeze thaw, that can raise the pressure enough to break things apart. So I think we need to be looking at things that aren't saturated to understand damage mechanisms. But I'll cut off because I'm the voice from God and it doesn't seem fair. Okay.
everyone's sitting here looking very interested, except for me, who's standing here feeling slightly worried. I might need to add another chapter to the PhD.
Can I add to that?
Yeah, someone from the room.
Jonathan Taylor.
Oh, Jonathan, yes, John.
Calcium sulfate. So what is it? Can we actually, if we're going to do that,
Where is the mobile?
Yeah, we need the mic.
There we go. It's just come to him.
Excellent, thank you.
Robin's suggesting trapped air, but which is being pressurized by something. So the question is also what's pressurizing the air?
Yeah.
What I would be looking at is calcium sulfate from the sulfate skin from the limestone trapped in the pores. But that's
Yes, that's my theory as well. So historically, there was a lot of air pollution in Cardiff, a lot of acid rain. And when acid rain falls on limestone, it reacts and you get the calcium sulfate. And it's the classic black staining on Portland stone in sheltered areas where it's not washed off by the rain. If it is being washed off by the rain, it's being washed. It's entering the pore structure as it runs down that building. And in this case, I think the porosity of the terracotta was very fine. So when the wall entered a drying phase on a hot summer day, which we do get in Cardiff occasionally, the water in the wall was slowly migrating towards that terracotta, which was holding on to its water, and the evaporation was happening at the surface there. So all that small amount of calcium sulfate on the face of the limestone wall was being drawn in and concentrated in these small terracotta moldings. And then as that water continued to evaporate and dry, the calcium sulfate crystallized and expanded and cracked. I suspect freeze thaw probably didn't help because there was a blocked gutter. And I am now thinking very, very hard about compressed air.
It's interesting. I can send you some interesting work that was done, for instance, by Ianu with Chris Hall up and Bill Hoff up in Manchester. I think it's one of the things we've not been taking account of enough. And this is the problem with things like the rylum tubes. I always forget what they're called again, aside from rylum tubes. The Karsten tubes.
Yeah, Karsten rylum.
Yeah,
same
that's
thing.
right, because that's very unlike rain, and so it saturates the pores in a way that it
Is
might be telling
unrealistic,
us. Yeah, exactly. It tells us something. It's not saying that they don't tell us things, but they might be telling us something slightly different. It's how we interpret what we're getting, I think. But I've got some very interesting, if this is time for questions, I've got some interesting questions coming in and some interesting observations, but I don't know if you want to keep going, Patrick, until you've finished what you want to say.
Get to the end and we take.
This is it. This is the
Yeah.
end.
Oh,
This is
okay.
it. This
So
is the
here we
end.
are.
Yeah.
Fine. Great.
Sorry, I can see the next slide coming up and it just says wrap up on it. So
Robin, George.
To ask the questions that you've got.
Yes. I've got Paul. I'll start from Paul Beckett asking, in the terms of that decorative cornice, was there a frame behind it holding the terracotta in place?
On the glassworks, as far as I could work out, no. Some of the blocks weren't even infilled with concrete. They just sat there and just went straight back. The
Oh,
cornice itself didn't overhang that much. The building actually steps back quite a long way. And so the gutter is sort of set in above the line of the wall that's supporting it.
mhm. Very good way of getting water in.
It's an interesting choice.
Yeah. Yes, and John Fiddler is saying about the glasshouse brackets, buff-coloured terracotta is low-fired kaolitic material susceptible to acid rain impacts, which means calcium sulfate production. So we're back to that again, and crystallization of large salt crystals. And indeed, it's the size of the salt crystals that compresses around them the air. One
Yes.
thing that with you asked about the smaller capillaries, the absolutely makes sense that the salt crystallization would be occurring in those as things start to dry, because they have the most likelihood of the very fine capillaries are most likely to have their moisture flow path broken as they start to dry out, and that's where the salt will be dropped. So it
Yes,
makes
and there's also
sense.
a feedback system there as well, where the cracking creates these. The
Yes.
cracking physically appears as these very small capillaries as well.
Yeah. And
On the
I think the
buff
cracks are really
terracotta
important.
being weaker, I disagree.
Ah.
Some of the best terracotta in my data set is almost white. Some of the buff stuff is definitely weaker because they achieved that color by underfiring it. Some of the other ones appear to have been fired extremely well, and the amount of iron in the sample and the color it ended up being doesn't appear to be as correlated as strongly as you think. And one of the possible reasons for that is the iron is starting to act as a flux in the production of, I want to say martensite, but that's a type of iron. What's the word I'm looking for? The slightly mullite, that's the one. Thank you. Iron can also act as a catalyst for the production of mullite and get dissolved into that. So you may have in very well produced terracotta, it gets paler as the iron gets sucked in. That would be a subject for a different talk or paper.
Mind you,
So-
I've just I've allowed John to speak if he wants to unmute himself. John, did you want to actually take that up and so you can chat together about it? Silence from John.
So if you start to put in some china clay into the mixes, we suspect on some of the terracotta, does that have any effect?
So if you add china clay to the mix and you don't necessarily alter the way you're firing it, then you may get a slightly better ratio of alumina silica, which helps mullite production slightly earlier. But it fundamentally comes down to extra heat and extra time. There's a certain amount of heat work. And if you can't go above a certain temperature because your iron oxides start to decompose and go black and bloat and tear your thing apart, then you need to cook very slowly at a simmer for those reactions to continue. The other possibilities I've looked at, and this was all in the previous talk, which I don't want to recap now because that went on for about an hour and a half, was where you're including previously fired and ground up terracotta in the terracotta blend. They may be acting as seeds for mullite production as a template, changing the blend to include more kaolinitic clay it depends what you're taking out of the blend relative to that.
In itself, so we've got a research project.
I keep looking, and the more I look, the more I find I don't know. It's quite exasperating.
It's
So-
not
so-
just terracotta. It's a really difficult topic, I think. And
So-
there's a
so
lot going on.
Robin, do you have any more questions online?
Well, Michael Hill King is asking whether cast and tubes can be used on historic masonry with full confidence that there'll be no residue from the plasticine. So probably not
have-
full confidence is anything ever done with full confidence.
So you don't have to use plasticine. There are other options available. If you've got a reasonably strong bit of masonry or stone, you can even use hot glue, although you'd have to use a glass casting tube for that, not the 3D printed ones, they would melt. I have ended up with a trace amount of oil staining off the plasticine on one sample. That was a very pale sample, and it came out the oven and it may have been a little bit warm when I put the plasticine on it, so that was slightly self-inflicted. The oil is weaker in terms of contact angle than the water, so rain will always drive that oil out over time anyway. It won't be a permanent stain. I accidentally marked a hotel as well when I was marking one, but that was just because I took the dirt off. So I left a little ring of clean on the wall.
The ring of confidence.
Yes. I went back a week later after it had rained and it had disappeared again, which is reassuring. Jonathan's waving. Are there any other questions online?
Not at the moment. And Michael King says, Hill King says, thank you very much.
I was really intrigued to hear your description of the crack in the terracotta as being, in effect, a fireskin. Could you just explore that a little bit further? What makes a crack? What's the variation in the clay that makes a crack? And why would you consider that to be like a fireskin?
So
Yes.
that was this sample, yes?
Yes.
So that sample's roughly the size of my fist. And that it's cut off a block which is huge. The entire block is about 400 mil by 400 mil. It is hollow, although it still has its concrete infill, and I have to hoik it around the lab every now and then wearing steel toe cap boots. It's just one corner off that. That crack in there is where it was slab built, and it's where two pieces were pressed together, and it looks great from the outside. You can't see the join, but it wasn't fully pressed back in. That was either trapped air or it just wasn't quite locked. So we found that crack when we cut it open. There's also a nice big pore up at the top as well. So that's in the clay. That's in the greenware before it goes in the kiln. And from the point of view of the atoms at the surface, they don't necessarily know if they're at the surface of a crack, which is only 5 million times bigger than them, or if they're at the surface of the inside of the block and the space in front of them is 400, 500,000 million times bigger than that. From the point of view of the atoms, they don't really know. And so a lot of the effects you get at the surface would occur anywhere where you've got that gaseous interchange occurring. And the fact it's happening on cracks inside the block means I think it is linked to that kiln atmosphere, which may in turn be linked to the amount of hydrogen in it, which is causing, or water in it, which is causing infrared scattering. So the heat can go around corners and be transferred around neatly. Some of the old manufacturing methods, they'd get the kiln up nice and hot and then basically throw a mug of water in. And you get a flash, which is that steam filling it, and all the infrared then being very evenly spread around. It's like putting 10,000 disco balls into your kiln and shooting a laser and everything gets spread. Does that answer your question, or did I go wild on imagery and move away from terracotta?
No, but my understanding, which is probably very out of date, was that the fine particles at the surface were more likely to have a greater interface with the natural fluxes, whatever those fluxes are, whether they're iron salts or whatever, which are making tending to produce a greater degree of fusion at the surface. And I think you're probably going to tell me that's all wrong.
No, it's not wrong, but it's not the only mechanism in play.
Okay.
I've looked at about 9 different potential mechanisms. Some of them are interacting with the gases to form interesting reactions. One of them involves sulfur in whatever fuel you were burning in the historic kiln that we don't have anymore, so we don't get that effect anymore. But that was causing sulfur reactions with the hydrogen. You're getting hydrogen sulfide, which is then reacting with raw iron on the surface, and we were getting hydrogen sulfide, iron sulfide eutectics, which is a fantastic word, and it just means 2 things that when merged together make a liquid at a lower temperature than either of them alone. And that's something that produces a very strong flux. I know about that because in ceramics, they tend to use these special cones of special clay that go in the kiln, and the cones droop at specific temperatures. Each one's made with a different blend. They had a whole line of them which were high in iron oxide, and they said, do not use these in wood-fired kilns, because what happens is they react with that tiny bit of sulfur that's available. The outside of the cone goes hard because it fires off very quickly, and your cone doesn't droop. It's formed this shell, and that's one of the sort of examples of what's going on with that. But there are other ones which are just straightforward. The clay particles breaking down, silica and the alumina stop playing nicely and forming nice structured plates. The silica goes off and joins all of its silica friends in a wild dance to produce glass, basically gluing all the particles together. And that isn't necessarily reliant on a flux, or it could be using a flux that's inherent to the material itself, in which case it would be occurring here.
That is so
Right.
interesting, Patrick.
In terms of the porosity
Yeah.
of the material, I was, from what you presented, I was wondering if you were suggesting, I might have got this wrong, but the fractured surface and the fireskin surface there wasn't too much of a differential between the porosity of those surfaces. Is that what you were suggesting?
Fractures
Is a suddenly much more than lines of the more than the defect when things. I guess doing something like this, yeah. So it would be really nice if defects in porosity. And so this is measuring porosity as such, this will be measuring permeability. So the mechanics of the process is looking. Yes. Material behind the fireskin.
Is there, you say there's a difference?
There is a difference.
There is there a, so behind the fireskin there's higher permeability?
Generally speaking, in most of the samples I've looked at, I've found something. So it's all academic caveats.
Yes. On most of the things I've
That's
seen, some of the stuff that's fired, think to a higher temperature. And I say think because that's currently in the lab and I'll know next week. Doesn't appear to be the case. And it might be because it's going to a higher temperature, they actually deliberately chose a more porous clay in the first place. Glazed terracotta tends to be deliberately quite porous. Because they need it to actually vent really well, and they're not so worried about the durability because they've got this perfect glaze going on the front. So it tends to have quite big pores, and those pores, big pores, also tend to be quite durable in terms of freeze thaw or trapped air because they don't get jammed as easily. But in terms of a building that you don't want water pouring through the wall, they may be not as ideal. And if you've got two different types mixed on the wall, or you've got limestone and terracotta, or you've got even different types of stone and brick, that mismatch of pore distribution will affect how that water moves, because the tiny ones will hold on to it when it's drying, and the big ones will let it through when it's saturated. Yes?
Thank you.
I don't know if I answered your question or if I
No,
just
you
sort
did,
of...
you did answer my question and then you gave me a further explanation.
I felt that was like a threatening answer. You know, you asked me a question, I'm just going to keep answering it until you stop questioning.
Although
Well, I think in this field, there's no such thing as a simple question, is there? So there can't be a simple answer.
Most 19th century terracotta made in the ceramic, in the potteries, or was there terracotta manufacturing around the country? And do you have different bodies basically going into the terracotta? Do you know that?
Did that come through online?
No, that's a direct question.
No, I meant in terms of sound. We're not getting any feedback off the other microphone, so I wasn't sure. The answer is yes, there were definitely different bodies. It gets quite complicated because molds were resold as different manufacturers set up and went bust. So you can have things that are stamped with one manufacturer and it's actually someone 30 years later reusing their mold third hand. There's been a lovely study using XPF, which is a bit like EDX. Sorry for all the TLAs, the three-letter acronyms. We shoot radiation and we measure how it glows in about 17 different ways. But the XPF one is hand mobile. It's used a lot in scrapyards for measuring the different metal content of things as they come in, whether they're brass or tin or whatever. And someone went round and shot a load of terracotta statues with it. And he found 4 of them were dirty, because XPF only measures the very surface. So we got a lot of information about what was growing on them, absolutely nothing about the terracotta. But the other ones, he was able to get the atomic ratios and say, well, these ones and these ones and these ones came from the same manufacturer or the same clay body. And likewise, I've got something similar appearing in my data set. There's a whole bunch which have come out very similar to each other, but one of them happens to be a detail off the manufacturer's factory. So we know that all of those were definitely made by them using that same clay body. I can go into more detail on this, but yes, it was a heavy material that wasn't shipped widely at the initial point, and then was shipped very widely towards the end, even as far as America. A lot of the early terracotta in America was actually made in the UK. And still is. One question.
Really just an observation, probably everyone here knows, but we're contractors and we do a lot of terracotta work, and there's 2 UK suppliers of terracotta left. So
Yes.
and even there now, yeah, they supply a lot to America. So
yeah,
it has its challenges, cost and program wise.
I'll ask you a question about the difference between terracotta and faience.
Right. Yes. So faience is now I'm a Brit and I love Britishisms, and I've grown to really detest the use of the word faience. The Americans call it glazed terracotta, and that is so much more straightforward. Faience is the British, Michael's wincing at me.
I'm nodding though. I had to try and do this in the book. It was terrible.
Faience is the term for terracotta bodies with a glaze. And it's called that after, I think, a small town in Spain that used to produce leaded pottery ware, which was what was used as the first recipe for the glazes used on the building terracotta, where at least people aren't licking the building, so that lead isn't transferring quite as quickly. I do actually have one of the samples in the lab is in a little sealed bag with lead ? Written on it. I haven't tested it because grinding it up to test it means potentially grinding up a lot of lead, which I don't really look forward to. So I'm working my way around that one. That's sorry, I'm going off on one. That's the main difference. Faience has a glaze. It tended to come in a lot later, sort of 1920s onwards, when it became a bit more economical to make, when they could do it in single firing. Initially, they had to fire things twice, once for the biscuit, once for the glaze. That was twice as expensive for fuel. Then they figured out how to do it on a single fire. So it came in at about that point. It's a really nice material. It seems to be very durable. It's lasting rather well.
In the Historic England book, they actually referred to the early parts of faience is about models and pottery. It's not so much about faience as we know it.
Yeah. And I don't think it's a useful explanatory term. Glazed terracotta is quite straightforward.
I'll
And-
change all my report. So, Robin, any other questions?
Not at the moment, but I think that I have one about the faience glazed terracotta as well. I love to hear you weigh in on, you both of you, on what that means in terms of fireskins. What do you see if you take cross sections of the glazing?
I'll show you.
Yes, because that first one was glazed, wasn't it?
It is glazed. It's the one that has lead question mark on it, because that
Yeah.
really white thing is coming up in very, very
Yeah,
dense
very-
on the CT
yeah.
scan. That one is, yes, that's Victoria Palace Theatre. It's a white glazed terracotta. It's got a white base as well. So but it's been very well fired. It's a good strong terracotta, even though it's not red or buff. There are 2 Victoria Palace Theatres in London, just to be clear. This is the white one. I don't know. I received a pallet with.
I think the answer is yes. Actually.
Yes. Okay. Thank you. I don't know if this particular one is Carrara ware off the top of my head. Carrara ware was a particular brand of glazed terracotta that was used extensively in the UK in the 1920s by Dalton. If you have been through Bristol train station or Cardiff train station, all of the station platforms are Carrara ware, I think. It was used on the GWR as part of their stuff they could put in train stations that will get filthy from steam engines but can be washed easily. Sorry, Michael.
No. If there are no more questions, I think. Oh, Charles.
About that question you are on scales. Sorry. Question asked about at the beginning that isn't terracotta hollow and brick solid, and you said you'd come back to us and tell us why you disagreed.
Did I say I was going to come back to it, or did I just say leave it till later? So one of the things I want to do at some point is actually produce like a little graph or a map of different objects I've come across, which are all made from quite similar material, and they have different surface area to volume ratios. So that can include things like thin tiles and flooring tiles. They've got quite a lot of surface area to body, whereas something like a brick doesn't, but also the ball pediment on top of a finial, on top of a building, has obviously got the best surface area to volume ratio you can possibly get, but that's terracotta. Large terracotta pieces that were built into the walls as load bearing do tend to be hollow and were quite often infilled, but not always. On Harrods, some of them are incredibly thin, almost to the point of tiles.
Well, what you're saying is that the terracotta that we normally see has a thickness of about 30 millimeters, and it's you get plates, yes, but certainly the terracotta there is 30 mil thick right the way through. So the drying time and the shrinkage and the firing later on are uniform across the whole thing. So it's about the production of why you have that thickness.
Yeah.
Technically, most people know what brick is.
Sorry, you need it. You need
Yeah.
to.
Speak to the microphone.
We're arguing about bricks and porosity again.
But like a Minton Holland's floor tile, I mean, where are you on that sort of graph of porosity and
You will have to describe that floor tile to me slightly better.
like the
Slightly
ones that are in the sort of the Houses of Parliament, you get yeah, the encaustic tiles. They're very dense. So how different, where are you when you have a brick piece of terracotta, one of those tiles? Is there a gradient?
Yes, that's the other thing. That's like the other line on the graph would be like the overall porosity. I've got some bricks in my sample data set just to sort of maintain an edge so I can see where I'm coming into something that's very like a red stock brick. And I do have samples that are unambiguously terracotta. They're a window jamb that was rolled as a sausage. It's been infilled with concrete. It's got exactly the same porosity as a brick and almost exactly the same porosity as a cheap terracotta flower pot.
Yeah.
So, and then going all the way down, we have things like black quarry tiles, which are fired incredibly dense. It always shows up as the extreme throughout my data set on everything. And it has a surface glaze that's something like 14% iron. Like it's actually got liquid iron sort of glazing it. It's brilliant. And that's definitely not terracotta, but some of the ones in the data set are moving towards quite similar to that. So there's a very wide range available, and I think there's more overlap between the classes than there is separation between items in the classes. Does that make sense?
Yeah. Yeah. No, thank you.
The person who studies population distribution is nodding at me.
Well, I
Here's-
think kind of. Sorry, Robin, you were going to say something.
Yes, I was just going to ask you both about repair. When you've actually repaired, say, a cracked original or something and put it back and it's exposed. In particular, I'm thinking of glazed terracotta because there doesn't seem to be currently a way of doing that doesn't fail.
I'm going to hand you over to Michael for that. That's not something I can.
The answer, Robin, on when we're what cracked terracotta, we've actually tended to stick it back together using wood glue. The reason we've been using wood glue is that the strength of it is less than the strength of the terracotta, so that if you glue it back with an epoxy, that it will be much stronger than the terracotta, and therefore you'll get another crack in the terracotta.
Yeah.
Whilst if you actually do it with a wood glue, then it tends to be softer, and if it is going to move and crack again, it will crack in the same place, and you're not losing more terracotta. It of course does change the permeability, but epoxy would too, that particular point, so you may get a local effect around it, but to date we haven't had a problem with that.
It's
And
interesting.
of course, the porosity in a glazed unit is a
It's
different kind of problem anyway.
yes,
Yes.
it's you're not talking about moisture coming in from the surface if you've got a glaze on it. But I'm obviously banned from using faience, and I just need to keep it for kind of these quizzes where you need difficult words.
A lot of
Any other
vowels.
questions? I know
Right.
Michael is keen to wrap up.
Right. In which case, I'd like to thank Patrick for his update on where his research is. It just shows how complicated it is going to be to get to a point where we can have terracotta blocks which can be trimmed without losing the durability of it. Because at the moment, the most expensive part of repairing a building tends to be the scaffold. And then it has to remain there for the 17 weeks or whatever that you're actually having to leave it there doing nothing before you actually get the terracotta to put it in. So that is one of the aims of the research project. It is very complicated, and I'm very pleased that actually Patrick's going into it in this much detail, but hopefully we'll get to a point fairly soon whereby we can actually say to the manufacturers, if you did this, then kind of we'll be able to trim it, and we can order you 100 blocks the same size, and therefore you can actually make the molds much more effective, and then we'll trim it on site. So, but it's a long way to go. It's a pipe dream I've had for a long time, but
And of course, the trimming is occurring on the sides of the block, which aren't the ones facing the weather either.
Mm.
but
But
it is
unfortunately,
always-
there are the ones where, since water will always travel along those interfaces, it might be better now that we use limes rather than cements to attach things. But the original, yeah.
I think there are lots of considerations, but it was a fascinating talk. I
Oh,
learned
yes.
a lot, and I'm sure everybody here has learned a lot too. And Jean would like to say something. Hold on, I'll come to you.
One last question from Michael Hill King.
The second question, if I may, how does the density and porosity compare between handmade terracotta and machine-made compacted terracotta? Does this presumed difference lead to a different failure mechanisms? And I think perhaps the ceramicists in the room can answer to the force with which you have to compact clay.
So I can't answer this generally, but I have, of course, looked at the Harrods blocks in quite a lot of detail because I've had such a lot of good support from Harrods and a lot of access to it. And they also gave me some spare blocks from repairs, which were modern, reproduced terracotta. It's not extruded rain screen stuff, which might be what Mike is referring to, but it is modern produced slip cast terracotta. And in terms of porosity, there was very little difference. They were in this, it's definitely within the same zone and within the same ballpark. The poor distribution, if I remember, I don't remember. I'm not going to try and quote that off the top of my head. It's in the file somewhere. I might follow that one up with you later. But I don't have a wide enough data set of modern terracotta really to answer the question, if I'm honest.
Yes, of the two suppliers, one hand presses and one.
Yeah, of the two suppliers, one hand presses
Pause.
and one pours. So they make it up as a very liquid and they pour it into a plaster mold and it settles out. And the other one starts with extruded clay, which is rolled into slabs, cut, pressed into the mold by hand and jointed. But both of those are coming through modern equipment. So if you're running it through a modern pug mill with a vacuum attached, it's going to be coming out very de-aired in the first place. I would be surprised if there was a material significant difference attached to the two methods. I don't.
You think similarly, you think the outcome of the block after the fire is very similar.
I think the mixture of different clays going in, I think the length of firing and the temperature of firing, and I think the conditions under which it's installed on site probably have more impact than the simple case of whether it's extruded out of a machine as slabs or poured as a liquid and settled.
Sorry, you're saying there's more significant variables.
Yes.
The manufacturer.
And I think there's more significant variables within manufacture as well. than compared to just those two things. Like if I was to go to my back garden and dig up a large amount of soil and try and make terracotta out of it, which might have happened, the stuff I produce, even if I put it through exactly the same machinery, would not have the same quality as the guys who have been working on these for 20 years, or 30 years, or however. They've been going for decades and decades, under different hats and different company names, but they've been. In terms of if you wanted to specify terracotta and you wanted to make sure you had something that was going to meet your needs, then you need to think about what you're asking for, because a lot of the current specifications are brick based and they're about strength and load bearing. And most of the terracotta we use, the load is almost irrelevant. It's much more about that porosity, the sorptivity, the long-term durability.
I think that raises a question we haven't done before, which is the specification. The British standards and American standards too are all about strength.
Yes.
And in my experience, it's almost irrelevant. But anyway, thank you all very much. And I think we ought to say thank you to Patrick too.
Patrick, that was fantastic.
And we look forward to the next update.
Yes. Thank you very much.
Thank you very much. Applause from the... Oh, we've got a raised hand from Laura. Laura.
It was a very good presentation and I thank you.
Thank you, Laura. I'm sure that, I hope they've left their mics on. I'm not sure they have, but I'll pass that on. And
yes,
excellent. Talk soon.
Talk to you soon. Bye.
Bye, everybody.
Bye.
Bye.